Okay, here we go again. I'll check that recording out and see what's happening. Okay, so for reviewing this, we've already talked a few minutes about, just for people who might have missed this, ionic compounds, aqueous, and covalent compounds, aqueous. Hey guys, please be quiet. Okay, I know things got a little crazy here for a second, but please. Okay, now as far as the covalent compounds, they are not like ionized. They are not torn apart. Okay, they stay as they are, intact with their covalent bonds. Okay, but they are surrounded by water molecules. Okay, now an exception I'm showing you right here is with hydrogen chloride. Okay, in case somebody missed this on the video, and as you can see, we have these two electrons that are equally shared between the hydrogen and the chlorine. Now, what happens is water is dipolar. Okay, and its polarity is strong enough that it can actually, well, let's just draw it like this. Here's your HCl. Okay, these are unpaired electrons, or excuse me, lone pairs of electrons on the chlorine. And what will happen is the whole electron pair will go towards the chlorine to give us chloride. Okay? And the hydrogen will now be an electron deficient to be a hydrogen ion. Don't worry about the mechanism. I was just trying to show you basically when it gets pulled apart, sometimes the electrons aren't, let's say, equally pulled. I mean, one to each atom. Sometimes it's called heterolytic cleavage. And both electrons go to just one atom, usually the more electronegative atom. Okay? So the thing is, this is an ionic compound. A covalent compound, but when you put it into water, what happens is it is no longer ionic. Excuse me, I'm sorry. I'm a little bit flustered about the recording, so let me just catch my breath here. So now when you see HCl aqueous, it doesn't mean hydrogen chloride aqueous. It is now hydrochloric acid. And you're going to have the H plus and the CO minus. Both of them surrounded by water molecules, just like with the ionic compounds. But this is an exception to the rule. And of course, you'll always see some exceptions somewhere. Okay, but basically, when you see covalent compounds aqueous, I'll put the camera back here to see this part. When you see covalent compounds aqueous, that means just dissolved. Okay? They are just dissolved, they are not dissociated. But as I said, this is one of those exceptions. So just, you see HCl aqueous, realize that that is ionized. Okay, I hope that wasn't too confusing, but I got thrown off track by this recording thing here. All right, any questions so far? We okay? All right, camera. Going back this way. There we go. All right, now, before we proceed into doing concentrations and such, there we go. Let's talk about electrolytes. All right. Now, first of all, electrolyte, well, the term comes from the idea that it can carry a charge. Like they talk about electrolytes in sports drinks, and as you guys have had some biology or physiology or whatever, you know that, basically electrical circuitry is very important to the human body and other organisms. And the idea is like if you take that thing I talked about before, like the two electrodes in a beaker of distilled water, you put more and more salt in, what happens is you start building up more and more conduction within that solution. Okay? So the basis of something being electrolytic, we're saying that it can conduct a charge, which means it does have charge carriers, which means we're talking about ionic compounds. Okay. Covalent compounds, aqueous, will not carry charge because there are not any ions in the solution. Okay? Which is, you might want to write this down if you ever see the term. Sometimes when you talk about covalent compounds, they'll call them non-electrolytes. okay, non-electrolytes, which means they won't carry a charge. They will not dissociate in water. They might just dissolve. Sometimes they don't, but sometimes they do. Okay, now let's get 3 examples up here. The first example we've seen before. You take sodium chloride solid. Okay, now, over the arrow I have an H2O. Those arrows in balanced equations, those are places where you can put all kinds of additional information. You can put temperatures for the reaction, pressure for the reaction. Some reactions are high pressure. You can put information about catalysts. All kinds of stuff can go above and below that arrow. All right, so right now I'm just putting down water just as a way to signify that we're taking the sodium chloride and dumping it into a beaker of water. And now we have sodium chloride aqueous. It's an ionic compound. It's aqueous, so that means it's dissociated and dissolved. Let's take that HCl, covalent hydrogen chloride, and bubble it into water. And now we've got this HCl aqueous, but now it is no longer, as I just pointed out, it's no longer a covalent compound that's dissolved. It's now ionic. So it's dissolved and dissociated. And the last one up here is going to be sodium hydroxide solid. Dissolve that in water. And now we're going to have sodium hydroxide aqueous. Once again, dissolved and dissociated. Now let's look at these guys here. We're going to get into acids and bases in this chapter. It's going to be a very brief summation of acid-base theory because next semester you go into it a lot deeper. But anyway, sodium chloride in water, is that going to affect the pH of the water? Thinking about going to the Atlantic Ocean and jumping in the water, do people scream and go under and die of all kinds of acid burns? No, they have a good time. Put that salt on your hamburger or whatever you'd like to put it on. You can do that. Not too much salt, that's bad for you. But at the same time, salt, okay, it doesn't affect pH, it's neutral. So this is going to give you a neutral solution. HCl, well, it gives you hydrochloric acid, so we can tell without too much thought that's going to be acidic. Sodium hydroxide. Hydroxide is very basic. So right here, we have neutral, acidic, and basic. All right? Now the thing is, as far as electrolytes, we can have acidic, which we call strong acids. Okay, I'll put that right here. It's going to be a strong, I'll get the camera, acid. I know I'm probably beyond that a little bit. There we go. A strong acid. And the sodium hydroxide we'll call a strong base. Okay, now we'll revisit that very soon in this chapter, but I thought this is a good time to introduce this stuff. Now, we'll just call this a neutral salt, the sodium chloride. Okay, now notice I have strong acid, strong base, and this guy is also a strong electrolyte. We put this up here, strong electrolytes. Okay, you can have strong acids and strong bases. And normally they don't say strong neutral salt, they just leave that alone. Okay, now why do you say strong? Okay, well we throw strong into the mix here because a strong electrolyte totally dissociates. Oh, excuse me. Say completely dissociate. Okay? In other words, if you have, let's say, 1 mole of sodium chloride, okay, you put that into water, and now you'll have 1 mole of sodium ion and 1 mole of chloride ion in solution because it totally dissociates. Does everybody see what I'm saying there? Put that down just a little bit. Does everybody get that? You'll have 1 mole. It totally dissociates. And the reason we have to basically note this is because some electrolytes, especially some acids, do not completely dissociate. And those are called weak acids. We also have weak bases, which are a little bit more roundabout in description. But the idea is you don't get a total production of, let's say, sodium and chloride ions. And more importantly, when we talk about strong acids, okay, let's see the HCl, and once again we'll say 1 mole of HCl. You put that into water, and you'll get 1 mole of hydrogen ion and 1 mole of chloride ion. Okay? Does everybody get the idea of 1 mole of HCl gives you 1 mole of each? Everybody okay with that concept? Because sometimes when it comes to dissociations, people get a little confused. Okay. So these are strong acids, strong bases. I'll talk about them a little bit more when we get to the acid-base theory in the chapter, but they're not as direct in definition as these guys are. Okay, so electrolytes, strong electrolytes, and as an example of a weak electrolyte, let's talk about a weak acid. This question? Yeah. Okay, I'll come back to that just in a second, okay? Let me just finish this thought here. Weak acids. Here's an example here. Let me put this up a little bit. Camera should be fine. If we take this guy, I've talked about him before a little bit. This is acetic acid. Okay? You take pure acetic acid, put it into water, and you're going to get a dissociation like this. Okay, don't worry about these. We'll come back to that. Just kind of jot it down. It's not going to be that important at this time. Okay, so you put the acetic acid in water, and that's what you get. You get a dissociation. This is called, can anybody name that ion, by the way? If it is acetic acid, what do you call the ion? Acetate. Very good. Acetate ion. Okay, and that's, of course, hydrogen ion. Okay, here's the deal. We won't get into this a lot this semester. In fact, I'll just mention it. But what happens here is that this is your forward reaction, but in this case there's also a reverse reaction where the acetate and the hydrogen ion come back together again to form the molecular acetic acid. Okay? And now it doesn't go all the way in one direction and all the way back. It's two things going on simultaneously. Okay? And the thing about an equilibrium reaction, and next semester you'll have 3 chapters on this, so you'll get to know it very well. When a reaction reaches equilibrium, the only thing that's equal is the forward rate of reaction and the reverse rate of reaction, not the concentrations of reactants and products. Okay? I'm not going to go into this a lot, but just to give you an idea, just to kind of clarify this, you won't be examined on it. Let's say this represents reactants. This represents product. Okay? In an equilibrium reaction, you could have equal concentrations of both. You could also have a much smaller concentration of reactant and a larger concentration of product. Okay? Now, in this case, for a weak acid like acetic acid, what you have is you have most of it in the form of reactant and just a small amount of it in the form of product. Okay? So in other words, for acetic acid, if you have 1 mole of acetic acid and you put it into water, just a small amount of it is actually dissociated. And when you get to next semester, you'll find out a lot more about that and how small that amount is. So most of it stays in the molecular form. So that's what I mean by when you have total dissociation, like HCl, 1 mole of HCl gives you 1 mole of hydrogen ion, and hydrogen ion is the name of the game when you're talking about acidity. Okay? When you're talking about a weak acid like acetic acid and all those what they call carboxylic acids in organic chemistry, you just have a partial dissociation. So you just get a fraction of a mole of hydrogen ion for every mole of acetic acid, and that's a weak acid. Weak bases are a little bit, I can talk to you about them a little bit, but they're not as straightforward as the acids as far as descriptions. Everybody okay with that? So we got weak and strong electrolytes, acidic, basic, and neutral. All right? All right. Okay. So we got that down. Let's get, oh, you had a question about, yeah. In fact, I'm going to address yours right now because we're going to be talking about concentrations. So that will hopefully clear this up. And if it doesn't, we can go back to it and do some more. All right, let's get the camera all the way over to here. And there it is. All right. To kick off this thing about concentrations. Okay. I'd like to first talk about this concept we just mentioned here. Okay. Just to repeat it here. If you have 1 mole of sodium chloride, okay, well, you can see each unit of sodium chloride is 1 sodium ion and 1 chloride ion. So before we even talk about moles, let's just keep that in your notebook if you like, but below it you could write down 1 dozen, oh, yeah, 1 DOS. Hey, it's not that funny. 1 dozen sodium chloride units. Okay, so if you have 1 dozen, how many sodium ions are in that dozen of sodium chloride? How many? Yeah, a dozen. Right. So for this, we'll have 1 dozen sodium ions, 1 dozen chloride ions. A grand total of 2 dozen ions. Everybody can see that, right? Simple concept. Okay, but sometimes sometimes it takes a little time for it to sink in. Okay, dozens is totally inappropriate rather, when we're talking about such small particles. So what's the appropriate unit that we're talking about? The moles, yeah, the moles. So here we're going to have 1 mole of sodium chloride. That's going to be 1 mole of sodium ions, 1 mole of chloride ions, 2 moles of ions. Okay? Is that better? All right. So let's just move on to one more thing here, just to make sure, because that's very simple. Let's just move it up here just a little bit. Okay. Yep, I'm going to get my chalk out here. Come on, come on. There we go. So if we have, okay, what's our total number of ions in 1 mole of this? So let's say 1 mole. Now let's make it interesting. Let's say 6 moles. 6 moles of aluminum oxide. Take it out and break it down. How many moles of aluminum ions? How many moles of oxide ions? Well, what do you think? If we have 1 mole of this, we have 2 moles of aluminum and 3 moles of oxygen. Does that sound right? See, this indicates how many of each of these ions we have. So if we have 1 mole, in fact, let's just do the 1 mole thing, then we'll move into 6, in case somebody's not seen it yet. If we have 1 mole of this, then we're going to have 2 moles of aluminum ion, and we're going to have 3 moles of oxide ion. Does everybody see that? Just look at it. Everybody see it? Don't sit there quietly if you don't. Yes, sir.
Can you just say that again?
Sure. No. Thank you for bringing it up. Yeah. Oh, 'cause people are going, I don't know. I'm just going to go home and it's going to sink in. Yes, this lecture will follow me home while I'm asleep tonight, and I'll learn it. Yeah. No, but thank you for bringing it up. Okay, you can see if you describe this empirical formula, which is what it is, you'll have 2 aluminum ions, right? 3 oxide ions. Okay? We got that. Okay, so if we have 1 mole of this unit here, that means it's going to be, well, 2 moles of aluminum, 3 moles of oxide. Does that make sense? Okay. So let's kick it up to where we were before, and suppose we have 6 moles of aluminum oxide. Now do the math and tell me how many moles of aluminum ion, how many moles of oxide ion, and the total number of moles. Somebody got real anxious. What's the answer? Wow. I heard 12 aluminum, so that'd be 6 times 2. And how many oxygens? 18, which gives us a grand total of 30 moles of ions. We okay now? The reason I have to go through this is because when you talk about concentrations, and part of that's going to be concentrations of ions, okay, when things dissociated, floating around. So is everybody okay with this concept? You better now? Okay, good. Okay. Now you can go and have a good time this weekend, right? Good. All right, so that in mind, if we're okay to get to this idea of concentrations, we're going to talk about something called molarity. Molarity, which is a capital M. Molarity is defined as the number of moles of solutes. This is where these little definitions come in very handy. Moles of solute over liters of solution. I'll spell out solution just in case. Solution, there you go. Okay? Not liters of solvent, liters of solution. Okay, so we got to keep these terms straight. There is a concentration term where you do use solvent in the numerator, or denominator, excuse me. But you'll get that next semester. Okay? So anyway, molarity. To move ahead with this, we have to go back and recall the definition of a solution. I heard it the very first response in class. It's a homogeneous mixture. Okay? You have to make sure you get these definitions down, you understand really what's going on. Okay, let's say we have something here. Let's keep it simple. Sodium chloride solution, 1 mole per liter. Camera, thank you. There you go. Regardless of where you sample this solution, if you put like a pipette in there and take some off of the bottom, you take some up here, you take some in the middle, the exact same concentration, uniformly dispersed throughout. That's an important concept here. Okay? So let's say this is a 1 liter container. Okay? 1 liter container. Now, if I define that as 1 molar solution, how many moles of sodium chloride are in there? Simple. 1 mole. Mole per liter. 1 mole per liter is 1 molar. Okay? And that's also what they say. So a molar solution means molarity. Okay? And it's another term they use. Bless you. All right. Now, suppose I poured off half of that, half a liter into another beaker, another container. How many moles would be left in there? Half a mole. Remember, it's uniformly dispersed. If you pour off 1/4 of this, you're pouring off 1/4 of a mole. If you pour off half of it, you're pouring off half a mole. The concentrations will stay the same. If you don't believe me, let's try it here. If we have 1 mole, okay, sodium chloride in 1 liter solution, that's going to be a 1 molar solution. Now let's just say I pour half of it off. So now I have 5/10 of a mole of sodium chloride, that's supposed to be chloride, excuse me, in only 5/10 of a liter of solution. Well, we still have a 1 molar solution. See what I'm saying? We haven't done anything to affect the concentration. Now, the thing about being able to pour off a certain number of moles is very important, because some of our chemistry, we're not going to go into a jar and take out dry chemicals and weigh them out. Okay, we have to have so many moles. Sometimes you're going to go to a stock solution and have to, and have to measure out a certain volume of solution to transfer the number of moles that you need. Okay, like if we had this as like a bottle of stock solution, 1 liter, and I said this, let's say you're putting together a galvanic cell or something, and you need I don't know what, maybe a cell, and you need 3/10 of a mole of sodium chloride. How much of that would you pour off into another container? 3/10 of a mole. What? No, if you needed 3/10, you just pour off like, well, this case, this would be 1,000 milliliters, right? So you just pull off 30 milliliters if you needed 3/10. No, that'd be 30%, excuse me. What did I say, 3/10? 3/10 of a mole, right. That'd be 30%, yeah. So the idea is that we'll do some calculations in a little while, but I want you to just get the idea that, sometimes you'll be using solutions as your reagents that you're pouring into a reaction. You have to know how much to pour in to get that number of moles. But this is where all those definitions, you have to really understand when they say a solution versus something else. Heterogeneous mixture, let's say. Okay? So everybody's okay with this concept? Didn't mean to bore some of you guys if you really had it down pat, but sometimes it's this very fundamental stuff people don't get for a while. Okay, now let me come back here where you guys just think about what I said, and let's do some work with this. "15 minutes to go. And then you'll be finished with chemistry, at least I think so, for the day. Finish up a lab. Lab's going okay? Silence, snickering. I hear people shuffling out the door when I say that. How's that lab writing going, by the way? Do I hear groans or just kind of like, okay? No, if it's going, okay, that's great. Is it going okay? I feel better, thank you. Lie to me if you have to, just make me feel good. All right. Camera. Okay. All right, let's get back to molarity here now. Let's see. What is the molarity of a solution? Oh, let me put something before solution. Of a 1.5 liter solution containing 0.75 moles of potassium sulfate. Why don't you guys do the math? Because I have to dig up my calculator. I thought I took it out. And that's my cell phone. That's not going to work. Here we go. Well, I mean, it could work, but... Yeah, just work out that real quick. Moles per liter. That's all you got to remember. I guess that looks all right. Excuse me. Okay, let's move this over here and do the problem. Okay, I see what we got here. Let's see. We're we have 1.5 liters of solution, 0.75 moles of what we can interpret as the solutes. Okay, we're talking aqueous chemistry throughout this chapter. Okay, so recall that molarity is just going to be moles, solute, that's an EU rather, liters, solution. So the concentration here is we're just going to take 0.75 moles of, in this case, it's going to be potassium sulfate, divided by the total concentration here of 1.5 liters of the solution. Okay? What'd you guys get? What's that? 0.5. All right. 0.5. This is how you'd write it. M, and then potassium sulfate. Okay, that's how you interpret that. That means the concentration of the potassium sulfate solution is 0.5 moles per liter of solution. Okay, so as far as doing these kinds of problems, it's just like when we were doing the stoichiometry problems. Sometimes they give you stuff in moles, sometimes in grams. So if I said, what's the molarity of this 1.5 liter solution containing, and I'd say 37.8 grams of potassium sulfate. Okay, just change it to moles of potassium sulfate. Okay? Now, another important use of concentration, of molarity, is going to be as a conversion factor. Okay? In other words, you've got to find out, you know how many moles of a particular reactant you need, and it's in solution. So what you have to calculate is how many milliliters or liters of that solution you have to pour into your flask to transfer that number of moles. And in that case, we will use the concentration as a conversion factor. Okay? Now, some people will come back and say, why can't you just substitute in like this? I'd rather use conversion factors myself. Okay? So let's say, just make up a number here, 2.35 moles of, give me something here. How about calcium nitrate are needed, let's see, from a 2.50 liter, let's see, we'll make that 5.0 molar solution of calcium nitrate. How many milliliters must be poured off, or transferred is probably a better way to put it. Okay, so I kind of rushed this one. I'm sorry if my wording wasn't great. 2.35 moles of calcium nitrate are needed, period, okay, for a reaction. Now, it turns out you have it in the form of a solution. So you have a solution here, okay. In fact, for this, you don't really need this information here, okay. You've got the concentration of the solution. In fact, I kind of jumped ahead to something else here. Right now, put this on hold, okay, that I gave you that information. Just ignore it. That's why I put that up there. Okay, so you have 5 molar solution. How many milliliters must be poured off to get this number of moles of calcium nitrate? Okay, does that make sense? Like I said, I'm getting kind of pressed for time, so I kind of speed things up a little bit. My apologies, but this is Power of Friday, right? All right, so let's see, what do we need here? We need 2 point, what? Is the camera over? Yeah, camera's over. I heard a murmur. I thought I messed something up here. Giggle, giggle. Oh, no wonder. Goodbye. All right. All right, fresh piece of chalk. Yeah, watch my spirits change. There you go. Okay, now we need this many numbers we need this many moles, 2.35 moles. Okay? Now, we'll take our 5.0 moles per liter. Now, notice if I say 5.0 moles of calcium nitrate per liter of solution, we have both moles and volume. Let me move this over this way a little bit so we can see that. In this concentration here, we have two separate units. We have the moles, okay, that's an amount, and we have a volume. Okay, two separate things here that we can now use to convert from one to the other. Always look for that. That'll give you your conversion factor. Okay, so if we come back here, let's go back up again. We'll put moles underneath and liters of solution on top. Okay, so it's going to be 5.0 moles of calcium nitrate per 1 liter of solution. Moles are going to cancel out. And then all we do now is just divide one into the other. So we'll have 2.35. Oh, geez, my calculator. Come on, don't do that. There we go. 2.35 divided by 5. And I come out with 0.47 liters of solution will be needed. Now, in the problem, I asked for milliliters. So how many milliliters would that be? 470, right. 470 milliliters of solution are going to be needed. What do you guys think of this? Is it okay? Yeah, just recognize, pull out conversion factors wherever you can, okay? And use them, because when you see the unit, okay, we got 5 minutes, guys. So wait a minute, take your parachutes off, okay? Just wait a minute here. You have to put your trays in the upright position yet. The flight's not over. Let's just talk a little bit about how we make these solutions up. All right? In fact, this would be a nice, relaxed way to end the lecture. Let me get back on camera. There I am. Okay? Anybody can recognize this? Anybody says a vase, leave the room immediately. Anybody says a flask, if you're thinking about chemistry flasks, you're correct. I'm not sure what kind of flask that could be. Anyway, this is called a volumetric flask. Now, this one has a number down here. It says 2,000. That means when you fill it up properly, you'll have 2,000 milliliters or 2 liters of solution in here. All right? Now, every volumetric flask, they state a volume, and then up the neck, there is a hairline etching in the neck. Okay? Now, when you fill this flask up and you watch the meniscus, it's important you do this properly. You watch the meniscus, and you fill it just as when the meniscus hits this line properly. That'll be 2,000 milliliters very precisely. Okay, a lot more than you get with a graduated cylinder. All right, so this is what you use when you have to make, let's say, pretty precise measurements on solutions. And just to give you an idea, I think the book has a little, yeah, they do have some pictures of this. But if I had to make up a certain volume, let's just say let's say a 2 molar, let's just say 1 molar volume of sodium chloride. Okay, so this is a 2 liter solution, so I'd need 2 moles of sodium chloride in 2 liters. Is that correct? Yes, it is. Just go like this and I'll keep talking, okay? So what you do is you get some of your dry sodium chloride and you just pour it into here. And then all you do is you fill it about maybe 1/3 of the way up, about that. And the great thing about these things is there's sloshability. You can go like this to mix them up and it stays right in the bottom, okay? You don't want to wait till it's filled all the way up before you start shaking, okay? So you get it all dissolved with about maybe 1/3 of the amount of water in it. And then what you do is you very carefully fill it up to here. And then you've got it. That'll give you your 2 liters of a 1 molar solution. Now, here's the thing. If ever you're using this stuff and you're kind of in a rush like me right now trying to get this lecture done for Friday, and you all of a sudden overshoot it, okay, you hiccup or somebody comes in and slaps you on the back, and all of a sudden you put, a little bit more in than you should. You can't do this and pour it off, okay? Because you basically, it's all that extra amount you put in there is already part of this, and it affects your concentration. You got to pour it all out, start with a clean flask, and begin all over again. Okay? But this is the idea. Next lecture, put your parachutes on. The next lecture, we'll talk a little bit more about making up these concentrations and then getting some chemical reactions. You guys have a good weekend.